is the method known as GMM, Generalized Method of Moments. Well, for simple application, it's not that difficult. But when it comes to more a real problem, a bigger scale problem, it may be a little complicated. But let me show you from the simplest framework first, and then we can think about how far we can go from there. The simplest kind of situation is to run a regression, linear regression. So it could be a simple regression without intercept term, or it could be a multiple regression. Okay. And ordinary least square estimation is to basically calculate this quantity and minimize it with respect to beta. Okay. But what we got here is the variance of this guy. Right? Because as you can see, the epsilon is this minus that, right? This minus that. And squared and calculating average. So that's excuse me, variance of epsilon t. I'm still struggling with my flu, and today, perhaps tomorrow, is peak. So the least square method tried to minimize the variance of these residuals, right? Then how do we get from there? Well, we first take first derivative of this objective function with respect to unknown parameter beta to get this expression, right? So what it says is expected value of this x times epsilon equals to 0. Right? So we have sample size like this, right? 1 through cap t. So at small t, you have a data, so unknown parameter and data, right? At t equals 2, you have another one, right? So you have cap t of them. So taking average, so add them up and divide that by cap t. That's the expectation, right? So for this to be the estimate in this framework that minimize this one, then this condition has to hold. So we call this one as a moment condition. Okay. So as you see in front, the title of this lecture note, Generalized Method of Moments, it has something to do with moment condition. Okay. Obviously, this problem is linear, right? Linear. But sometimes your objective function, your moment condition may be non-linear in terms of parameters to be estimated. So in that case, general moment condition, and you may encounter the situation in which you have to estimate parameters given this moment condition, and also the relation could be linear in parameters or non-linear in parameters. Okay. Luckily, this problem is easy to solve because we have a single parameter beta, and we can rewrite this equation as this. Right? So this is the standard OLS beta equation estimate. Right? If this moment condition has no analytical solution like this one, then we only have implicit solution, right? Implicit solution. So in that case, still GMM can be applied to this estimating problem. Okay. if you note, this is the case. X is all data from time 1 through cap t, and y as well. So this is average. So if you plug in that to there and xt transpose there, then you get usual formula, like beta hat. This one. Okay. Then what is the formula for the variance of this one? We need to calculate this variance to make some inference, right? This is basically the a general formula for the variance of beta. You estimate it. When you look at this one, it has some term here and some term in big square bracket and the other, right? And some horrible rotation enters from minus infinity to infinity, right? So probably may scare you off. But you don't have to worry about if the residual is identically constant mean and variance, identically and independently distributed, then you don't have to worry about this correlations. Okay. So this J counter runs simply from 0 to 0. Okay. So all terms drops out and just this term. Okay. Then as you can see, here some terms I think cancels out, right? This one and that one, right? So sigma squared and this term survives, right? So only this term survives because sample moment is computed in this way. So if you plug it in, this to there and take inverse, then this t cancels out and this sigma squared and that inverse survives. So usual formula for variance of beta hat is sigma hat squared x transpose x inverse. This result. Obviously, this one is from sigma hat squared is summation of epsilon t squared divided by t minus number of parameters. Okay. Then you're all done. What if it doesn't have any, it doesn't satisfy this condition? So this is the assumption of, this was the assumption of homoscedastic variance, right? But that could be not be the case. So if epsilon t is heteroscedastic, and this is a formula, instead of you don't worry about serial correlations. Okay, serial correlation. You just worry about different sigmas for different t. So it's there, right? You know that, ignoring this part, expected value of sigma t squared, that's the variance of epsilon t squared, right? So previously we assumed that is same for all epsilon, but it could be different. So let's leave it there as it is, and that's the white version of heteroscedastic consistent estimate for the variance. So we know that this relationship, right? So you plug it in here, 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 and then you get some operational version of this. But that is going to be lengthier than this one, right? Here is a situation we've seen already, but Hansen and Hardrick, actually, Hansen introduced this idea of general method of moments estimation, but his co-author Hardrick examined this predictive equation we have seen already. So this is RT K is overlapping return, K period overlapping return is regressed on a dividend yield, for instance, earnings price ratio. Okay. And we know that because this is overlapping return, so there will be a serial correlation, right? So epsilon t, single period return may be unforecastable, so it's random, but the covariance is not going to be 0 for j less than k. So if overlapping period is k, then k minus 1 serial correlation is induced because of the overlapping construction of dependent variable. Okay. So even if RT self single period return is random, if you are constructing k period return, overlapping return, and k minus 1 serial correlation is introduced, moving average serial correlation, right? So this is the case. But for more than that, it's going to be 0. So in evaluation of general variance formula, you need to worry about from minus k to k. Usually k is less than cap t. Right? So this is another operational version. So in 1982, Hansen and Hardrick tried to predict future overlapping exchange rates using some variable. And they to make inference whether this is significant, they have to calculate variance, right? But the variance is considering potential serial correlation because of this. And epsilon t enters as it is, right? That means potentially heteroscedastic disturbance term is also considered. That was about time I was preparing for my study in the United States, because I started my master's course in 1983. So when I got there, and when I tried to replicate their results like this one, I found that I can compute this quantity sometimes, and sometimes this quantity cannot be computed. And actually, probably Hardrick didn't notice that at that time. But when you work with different sample in other framework, if you consider this in this way, sometimes it may work, sometimes it may not work because of this. It is epsilon 1 through epsilon cap t, epsilon 1 through epsilon cap t. If you multiply these two, then there could be sigma squared, right? If there's no serial correlation, then this is a situation of classical least square. So in matrix notation, that's what they write. This is cap T definition. Heteroscedastic case, we don't have that. It's different, right? Because we don't have actual number, real number, so it is replaced by that, right? Also. So that's the situation. Still we have all zero. That's the white heteroscedastic consistent covariance matrix. The third one is to look at serial correlation. So you're looking at epsilon 1t, 1, and epsilon 2. What Hansen and Hardwick did is, on the null hypothesis of random return, because you're looking at k overlapping period, so there will be k minus 1 moving average terms. So they suggested this parallel line up to k and k. Those are considered. So serial correlations are considered. Okay. So if you look at a long overlapping horizon, and it gets wider and wider. Okay. In case if you look at everything, then up to cap t, right? Up to cap t. When we introduce notation minus infinity to infinity, well, if t goes to infinity, right, then that's the situation. But because we have only finite sample, cap t, number of them, so we look at this dimension, right? Well, later, several years ago, later, Newey-West found the problem that when they apply Hansen and Hardwick correction, sometimes the covariance matrix is computed, sometimes not. Right? So that's a real problem, practical problem. Right? So they thought about the situation where, well, serial correlation is okay. Okay, heteroscedasticity is considered first. Okay. Now, serial correlation is also considered. So adjacent numbers may be correlated, and signal could be strong, right? But as you move along this way, so current observation and next observation, current observation and the third observation, if the periods becomes far apart, then serial correlation may be smaller, right? So Newey-West is basically the same as this one, but depending upon which k, the value of k, they give different weights. So this one has full weight, this one has a little smaller weight, smaller weight, smaller weight. And by doing so, the failing case of this Hansen and Hardwick disappeared. So that's the contribution of this. because these are pretty much technical. You don't have to worry about all those algebra behind that. Just try to remember under what circumstance we need to use that kind of standard deviation, because those are all available already from EBIUS, for instance. Okay? So if you worry about heteroscedasticity, but the form of heteroscedasticity is not known, then White's estimator is one to calculate standard deviation. Least square estimate, the beta is okay. OLS, whether it's heteroscedastic or serially correlated, OLS beta is a consistent estimator. Right. So if sample size gets big, then it will approach to true parameter. So OLS beta is okay. The problem is standard deviation. Okay? So if this is heteroscedastic, then allow this one vary in this way, and that's White estimator. And if you believe that there is a heteroscedasticity and the serial correlation, then Hansen and Hardrick, or improved version provided by Newey-West. Okay. So usually Newey-West is pretty much a prevailing method these days. Okay. So let's take a look at a little more finance-related problem. This is GMM, and we try to test a single factor model. A single factor model where this is vector and this is actually a scalar. Okay, this one, ZTE in my notation, excess return vector. There are n of them. Okay, so for instance, if we have, let's say, all listed stocks in the exchange, we have about 1,800 stocks listed in KOSPI and KOSDAQ. Okay, calculate market capitalization at a particular point and line up from large cap to smallest cap. Okay? Then, count 20%, 20%, 20%. That's a decimal portfolio. So you can calculate new index with those market capitalization within top 20%. Using these stocks only, you can construct new index, right? And then second percentile, you can calculate another index, portfolio, and so on. So suppose you calculated n stock index according to the size of the company, okay? And then from those index, you can calculate return and subtract risk-free rate, and that's your excess return. Okay, excess return. This is a market return. That's KOSPI return subtracted by risk-free rate. Okay? So excess return is regressed by excess market return, but the dimension is n. Okay. So what I'm saying here is you have large cap and small cap. You have an index and its return, index and its return. Calculate excess return, run a regression of excess return on large cap on market excess return. The single equation, right? You can do the same thing for this one, right? But now we try to consider doing this one at the same time, together. So sometimes, this particular model is CAPM, a sharp internal version of CAPM, may hold for large cap, may not hold for small cap. But you may want to test whether these two are, the CAPM holds for this one at the same time, jointly. That's the scheme. Okay. Typical assumption is epsilon is 0. Covariance is finite. Actually, T transpose, epsilon T transpose. And this one, market excess return, and expected value is lambda, and we call this one market risk premium. Okay. Market risk premium. What is the variance of this guy? Well, excess return, market return, and its deviation from its average squared, and taking average, that's the variance, right? And we assume that these are not correlated. Because this is a factor. Factors are not correlated each other, nor with epsilon term. So, as you've seen from previous simple context, this is one of the moment condition. Right? Average is 0. That's first moment condition assumption. This could be another moment condition, right? Because if you run a regression of individual of this one on that, including constant term, you can calculate this one, right? So if you have all those epsilon sequence, you can calculate covariance matrix, right? And you may be interested in finding true value, population value, whereas you can calculate from the sample. Okay. So you may want to calculate this one from sample minus sigma equals to 0. That's another moment condition you can think of. Right? And here's another moment condition. So depending upon your problem, sometimes you need this as a moment condition if you're interested in variances, covariance matrix. But in our case, we are interested in these two parameters because CAPM states that excess return is linear or proportional to market risk premium. And the proportional vector beta is there, and this alpha is 0. Okay. So a sharp internal CAPM test is, if you have small cap, large cap, or individual assets classification, and if you have n of them, some equation has alpha that appears to be significant, some aren't, some significant, some aren't, right? It's mixed, right? So what you want to do is you want to test whether alpha jointly are all 0. So this is our situation here. So if that is a situation, you need to, you have n number of alpha parameters to be estimated and n number of beta parameters to be estimated. Okay. So let's call that as theta, 2n times 1 dimensional vector of parameters. Well, then the moment condition we'll be using in this case is this one and that one. Okay? So take a look at this. This one and that, this one and that, for n equals to 1. N equals 2 or n equals I, and n equals to cap n. Okay. So, can you gauge some dimension of the problem? This is at t. Our sample run from 1 through cap t, right? So this is a snapshot at t, small t. There you have pair of moment conditions for each asset, right? Each asset. So the dimension of the whole thing is 2n times 1, 2n by 1, and number of parameters to be estimated are also 2n times 1. Right? So if you have moment condition, number of moment condition is actually same as number of parameters to be estimated. The problem is exactly identified. Sometimes you may have more moment condition than number of estimate, number of parameters to be estimated. Then in that case, we say it's over-identifying restrictions. Of course, if number of moment conditions are smaller than number of parameters to be estimated, then that is underestimation, under-identified case. So you can identify this one separately. Okay. So you need to have at least exactly identified moment condition or over-identifying moment conditions to start with. Okay, so this is the one when we talk about population, but we have only a finite sample. So basically, this one is something inside this, right? Inside this. So we take covariance or this here expectation. So expectation of f, and that should be 0. Okay. Where theta 0 is something true parameter. Then let 1 and GMT superscript E, that is, let's call that H. And using notation Kronecker delta, O times thing, f of t, you can write it in this way, or believe it or not, you can write it this way. The same thing. Okay. What is that? If you have two matrices A and B, Kronecker delta, Kronecker product is when you apply this one, you multiplying this matrix to every element in A. Every element in A. So you are multiplying this one in every element in H, right? Every element in H. What is H? This one and that one, right? So epsilon is multiplied to there. Epsilon is multiplied to there, right? Every element there. So epsilon multiplied to this constant corresponds to this term, this term, this term. Epsilon multiplied to this one corresponds to this one, this one, this one. Okay. So if you read the econometrics textbook, they usually express things in this form, but that's basically the same as this one. The sample moment this has to be equation 10, right? This one. Yeah. The sample moment of equation 10 is, of course, if you can calculate f of t. So this is just notational convenience. This is for notational convenience. When you actually construct f of t, you have to construct it in somehow in this way. Right? So when you have that, because your sample is finite, so take the average to calculate expectation. Okay? Then, so you start with alpha, beta, theta, right? You started with theta. Now you can calculate g of t. As this one, right? Or above, you calculate this one, right? Then, because we have number of parameters 2n times 1. So this is 1 by 2n times 1. 1 by, this is 2n times 1 vector. This is 1 by 2n. So this has to be 2n times 2n, right? 2n times 2n. So the GMM, the first pass of GMM is to minimize this quantity, setting this W, the weighting matrix, as identity matrix. So this identity matrix, so actually this is sum of squared, right? Sum of squared. Then it is known that that theta from this first a single one-time minimization problem, theta is consistent and asymptotically known. Then, according to Hansen, 1982, how to calculate the covariance of theta, GMM estimate theta, using finite sample t, well, this way. What has shown is this one will approach to true parameter with this speed, this rate, and this distance scaled by square root of t, this distance is normally distributed, on average 0. On average 0. So that means it converges to that, right? And the variance is this one. So difference between true parameter and your GMM estimate scaled by square root of t, on average 0, and this variance, and it's normally distributed. So in practice, well, from minimizing this problem, you get theta t hat, right? That's your estimate. Then what is your variance of this one? Take variance here, variance. What is the variance? Well, this is constant, right? So it is squared, and you can bring it out of this variance formula, right? So t times variance of this thing, right? But this one is parameter, true parameter, so no variance, right? So t times variance of that, right? So we calculated the variance of this thing, and you said this is the one. That's what Hansen said, right? So what is the variance of this guy? This divided by 1 over t. Okay? Let me show you this one first. Yeah. This one. Variance is 1 over t, that, right? Then here is some technical aspect of the problem. Here, what is then D and what is S? Actually, S is the covariance here. So when you when you go back to this problem, the general formula corresponds something like this one. That corresponds that. And how to calculate that? Do you see? Ft was moment condition, right? So Ft is defined in such a way and set equal to 0, right? Set equal to 0. So it's like more like error term, right? Error term. So f of t calculated in a particular way. So epsilon or epsilon times z t GMT e. That quantity is expected to be 0. So it works like error term. So error times error, if n is 0, then that's variance, right? Expected value of error squared, right? That's variance. If error is -1 through 1, then that's error t minus 1, that's covariance. Concept corresponds to covariance, right? So this is autocovariance matrix. And D corresponds to the first derivative of sample equivalent of moment condition with respect to parameters. So, as I said, this S is calculated in this way. So these are all in matrix notation, so it looks a little complicated, but basically showing this structure. First, this part, main diagonal, is captured by this covariance thing. Okay. And off-diagonal terms, J1 through that, that's the covariance thing, right? Covariance thing. Where, because you are looking at covariance this side and that side, symmetric, right? So you have covariance this side and that side symmetric, so two of them. And then you have a weight. So maximum is J goes to Q. So 1 minus 1, right? So 1 minus, let's say, 1 over Q is the weight for first leg. And 1 minus 2 over Q is the weight to the second line, and so on. So basically that's what it is. But the actual dimensional problem you can figure that out if you actually start working, writing your own code. But that's something, a very tedious one. So hopefully you don't have to do it by yourself. You can use it from someone else's code. But definitely this is something you can make it operable as long as you get the idea about what is in fact is doing. Okay? So if you can calculate in somehow using Newey-West weighting scheme, if you can calculate this, obviously this is not that difficult to do it, using any function that calculates first derivative, you can calculate this one. So rest of them is calculated. So when you calculate this S using this one, using first stage estimate of theta. In the second stage, use that as inverse weight. So previously in the first setup, we have W, which is identity matrix. In the second stage, you have this one replaced by that. Okay? So it's like, story was like this. Okay, you have moment condition, 2n of them, right? Moment conditions. Something could be very close being 0, something may not that close being 0, right? When you set weight matrix W as identity matrix, then you are treating those equal. When you calculate S that way, then, depending upon, those errors could be close being 0 or far away from 0 and so on. Depending upon the value of appropriate S, a corresponding element of S, the weights are treated differently. So that's basically what it is. So loosely speaking, this one, S of t, is the variance of that. So what it does is, this is moment conditions squared divided by or scaled by its covariance. The scaled moment condition is minimized in this case. So when you repeat this, you calculate the theta and plug the formula to there, and then plug it there, and then minimize it, obtain theta again, and calculate theta again, S again, and you do that several times. Usually it approaches to the final estimate quite quickly. So that's the procedure. So seeing is believing. This guy named Cow, well, when I try to write my own GMM code, as I told you the other day, the first thing is not just sitting in front of a computer and start writing a code. First thing is to look around, ask around, surf, and find whether there is some program written available for me. Okay. When I did the Google search, this name came up, and he showed how to implement this GMM using MATLAB. And MATLAB is not my favorite computer programming language. Mine is Gauss, but MATLAB is much more powerful and have more users. So I started learning MATLAB and tried to follow. So what his sample program it shows how to calculate that Newey-West covariance matrix and all those in function. Okay, so as long as you know how to use it, you can use it. Okay, his sample program is to generate y given x and epsilon, and setting alpha equals to 1 and beta equals to 1. And generate some number and try to apply GMM estimation and calculate standard deviation. To make sure that I understand his problem, I try to modify his program by setting beta equals to 0, so suppressing net, and alpha is 1. I reduce the problem of finding 2 parameters to 1 parameters. Okay. Because 2 parameter problem, when I run it and it runs, and I don't know what's going on, so I try to change accordingly after assuming this one and see if it works, and I understood the program. Okay. So this is the sample time series. I uploaded it to my site in this file. Obviously, because beta is 0 and alpha is 1, alpha is 1, and no relationship, right? Just flat line, right? Flat line. So using this data, so this is the sample file, sample screen where he generates this data. So I brought it to the same data to eMuse and run a regression of y on x, and found we expect this one is 1, right? This one is 0, and as we expected, this is the case, right? This is the case. But in this case, I could make things more interesting by generating epsilon t from serially correlated sequence, or I could add some heteroscedasticity. I can design epsilon t that shows heteroscedastic movement over time and some serial correlations, right? Then the problem could be more interesting, right? But here, this is just a simple random numbers from normal distribution. So no serial correlation there. So we don't expect that estimating this one using least square or using GMM wouldn't be much different. Okay. But if you brave enough, then you can try. You can try with different sample data generating process and see if whether that kind of claim is in fact true. Okay, so we got this least square result, and then I run this chaos program, and I found this number to be 1.0123. So very similar, and this is Newey-West standard, Newey-West t value. So t value computed from Newey-West standard deviation of this estimate. Okay. So OLS standard error and Newey-West standard errors are slightly different. So Newey-West standard errors should be a little bigger than net, right? Making t smaller. making t smaller. But not, in this case, not substantial. My advice was to stay in EBUS if you can. So I looked at EBUS quick estimate equation, and there you can choose. We usually chose least square or non-linear least square, right, as a default, or arch for volatility model. But in EBUS quick estimate equation and method, you can choose GMM. That's just quick. Okay. You can write your dependent variable followed by regressors. Okay. I haven't tried whether you can allow. This is my first equation, so y1 x1, y2 x2, different c's. I'm not sure whether it allows to do that, but basically this one is equation by equation thing. So later you can read off this help file, see if that is allowed. Okay. So in this simple case, y on x, and it says what is the instrument? This well, here is a check mark, include a constant. So one constant is always included in GMM as an instrument. Okay. Do you call this one, right? 1. And this is regressor, right? Regressor, which is assumed to be orthogonal to error term, right? So I wrote this as instrument. Another way of saying it is, because we have single equation, right? Two parameters to be estimated. Right? 2 parameters to be estimated. Intercept term and coefficient, right? Then we need 2 moment conditions. Because 2 parameters to be estimated has to be matched by same number of moment condition, right? So one moment condition is using constant term. So expected value of epsilon is 0. That's the first one. Okay. Second moment condition is expected value of x times E is 0. So instrument 1, instrument 2. And 2 parameters to be estimated. So exactly identified problem. Right? It says estimation weighting matrix, Newey-West. So whatever it is, you can leave it there, right? So I run this one. This Bartlett corner Newey-West corresponds to, where is Bartlett? This guy is Bartlett. This scheme. This weighting scheme could be different, right? You can devise something different, but that's one. Parzen is another one. So, very similar coefficient and standard error. It says, it says Newey-West, So, in your typical multiple regression, y on constant and several explanatory variables, when you run a regression, you can always look for option from EViews. And EViews will ask you whether you want to change current default least square covariance matrix to white heteroscedastic consistent covariance matrix or Newey-West one. So even if you don't specify it from GMM, still, usual least square estimation, you can ask EViews to calculate this one as Newey-West standard deviation. If you suspect errors are heteroscedastic with serial correlate. I wanted to show what I've shown previously. I wanted to test whether return, risk-free rate, is alpha, beta, and market return, and epsilon. This is another CAPM. Market excess return, individual excess return. Apply to venture investment. This was the one I showed you. But if you look at the graph, typically, if you pick this line, this is annual version. So some venture investment made in 2002, there could be 50 projects or 60 projects. Okay. In 2002, on average, they started with initial investment. About 80% of total investment is made in first year, and about additional 10% in the second year, and then start receiving things quickly, recovered, and start receiving more than what they invested. So that's the typical pattern of this graph. Excuse me. So people want to know what would be the risk and return associated with this kind of net cash flow pattern. So by investing on venture, you want to invest. As a return, you want to earn big, but usually it takes time. Right? So we try to convert this problem into GMM estimation, where all you need to know is just similarity between this setup and the previous one. Simpler least square method. If you define this epsilon expected to be 0 if everything is right, that is your moment condition here. You want to make this guy or 0. Okay? Because you have finite sample, you have sample analog of this moment condition. So this is a G. So this is a G, and this is a weight matrix. In this case, identity matrix. Okay? And then the value that minimizes this function, if you have this one as an estimate, then use this one to calculate S, which is defined as this one. Or in this way. This is much simplified version of than Newey-West version, because my problem doesn't have any time dimension. So I don't have to worry about this, just heteroscedastic part. And then using that, replacing W, we can get this one and recalculate S and minimize it again and iterate it, and you get the result. Okay. And then the variance of this one is going to be, in our previous notation, it was 1 over cap T and this thing. But as I said, I have no time dimension, so cap T is 1. It's 1. So it disappears, and this one. Do you see? Because venture investments are not traded frequently. So I do make an investment today and receive returns after 4 to 5 years for about 2 to 3 years. So I don't observe frequent cash flow. So I cannot set up the model like this return on the left hand side. Then nevertheless, how to calculate expected return in that case? There has to be some way, right? So if I didn't make mistakes, basically when you consider cost P as a market, beta is very small numbers, 0.15. In the United States, they expect that number something like 2.7 or 2.8. But in Korea, we have very small beta. So it doesn't seem to move together with the market. It goes the other way around. But isn't it amazing that you don't even define, or you don't even have a data on return, but still you can run CAPM and estimate these two parameters. And these are, of course, Newey-West statistically consistent t values. And also, remarkably, when you set up this G or F of this thing, we don't know whether these error terms, a function of alpha and beta, whether the functional relationship is linear or non-linear. Still, it's okay. So in this setup, you are looking at things in this way, right? In this way. So whether there is a y minus x to the power gamma beta equals to e, you don't care. As long as you have parameters to be estimated and matching number of moment conditions, then you can solve it.